Checking sound. Hello, STAT students. I've tried to make this online experience as similar as possible to what was previously done in the classroom. At the advice of people much more tech savvy than I, we've chosen this particular method to give online lectures. This medium will allow me to continually show the PowerPoint slide and also give me the ability to speak and write directly below the slide, similar to what was previously written on the whiteboard. If you have questions, we'll communicate via email. It'll be important when you email me to clearly identify what lesson you are referring to and what slide you have a question on. This will prevent a lot of email tag and be more efficient for all. I have about 115 students, so this will be important. There's one big advantage with this medium in that anytime you can pause the video or rewind and run a portion of it all over again. I would suggest getting familiar with how to use that advantage. At the end of the video, you will be given an assignment to complete. Take a good and readable picture on your phone of that completed assignment and send it to the corresponding Dropbox. A second advantage will be the Dropbox for each assignment will be open for 2 class periods rather than 1 after the corresponding video for that section. Any assignment turned in after the second day of the class would have met will be counted as late. A final advantage will be you will not have to watch the video during what would have been the scheduled time of the class. This would certainly be an advantage for those living in the Pacific time zone. Otherwise, some would have needed to listen to the video at possibly 5:55 a.m. Each day the class would have met, you will be sent a URL address which will send you to a link from the cloud where you will access the video. We are told this method reduces the chances of overloading a bandwidth causing a crash or freeze. You will need to stay fairly current as the link will not be open indefinitely. Anticipate no more than a week past the scheduled time of that lecture. So please do not procrastinate as the availability of the link will run out eventually. It is important you realize college is still in session, even though we have given more freedom to when you exactly do that college work. Stay current as best you can. We will cross the procedure for testing later. So now I would like to begin using this medium. It'll be a new process for me as well, so please be patient. This slide should look familiar to you as we have seen it in the past. One of the things that we have done with confidence intervals is we have looked at large sample means. These are already in your notes. That would be when n is greater than or equal to 30. That formula was confidence intervals is our point estimate, which was x bar, plus or minus our z or t score. Because it was a large sample, it was a z-score, times our adjusted standard deviation, which for large sample means that adjusted standard deviation was usually going to be our sample standard deviation divided by n. We take the square root of that. That square root sign should have just been the square root of n. I apologize for that. So that would have looked like x bar plus or minus z alpha over 2 times s over the square root of n. We will review an example from that as well. We also have looked at small sample. Means. This would be where n was less than 30. The confidence interval for that one we have worked with before. It'll be the same sample mean, x bar, but rather than a z-score like we used here, it is going to be a t-score, which again should look familiar to you as we've seen it before, times our adjusted standard deviation, which would be s over the square root of n. This was again for n being less than or equal to 30. We will be reviewing those. We've also looked at formulas for determining a sample size for both of these, as well as what we're going to look at today, which is a confidence interval for proportions. To keep this consistent with your notes, I'm going to put that formula down right here. This would be for a large sample proportion. Large sample proportion. It'll be a confidence interval. Rather than a mean, x bar, like we had over here or here, we get our sample proportion, which we call p hat. We're going to have the same plus or minus a z-score. It's going to be a z because it's a large sample. So I'm going to now have plus or minus z, and that z-score will be found the same way it was found over here. My adjusted standard deviation for proportions is different. It doesn't have a standard deviation s, but you remember that adjusted standard deviation was a little bit different. It was going to be the square root of pq over n. And here the radical did go over the entire fraction. That's different than what you saw over here. What determines if this is a large sample or not is not n being greater than or equal to 30, but rather it is n times p had to be greater than or equal to 5, as well as n times q had to be greater than or equal to 5. We've done some work with those before, so that again should look familiar. Make sure that you have all three of these down, because all three will be expected to be mastered at test time. Let's review now the first two. You've seen these before, so they're not new to you, but let's review them. I highlighted in red a key component here, and that was that we randomly pulled 100. That 100 meant that n was greater than or equal to 30, so it was our large sample formula for this confidence interval. So I'm looking for a 95% confidence interval. It's going to be x bar plus or minus our z-score times our adjusted standard deviation. So in this particular problem, my x bar is the sample mean, which was 3.8. My z-score, you recall, is found by going to my chart, and I locate 0.475 in the midsection. It gives me 1.96. So that z-score is 1.96. The standard deviation is 1.3 given in the problem, divided by the square root of my sample size, the square root of 100. This will give me 3.8 plus or minus 0.255, which gives me my final interval to be 3.545 up to 4.055. That was our 95% confidence interval. Let's make sure we're again recognizing what this interval actually means. It means that we are 95% confident that the average number of hours they study on a given weekday is somewhere between 3.545 hours and 4.055 hours. This is not an interval for individual students, but this is an interval for the average number of hours from all the students in Northwestern student body. Now let's try one for a small sample. We're going to have that confidence interval. It's going to be the same X bar plus or minus a t-score times our adjusted standard deviation. So in this case, the X bar is the exact same number, 3.8. But what does change for the small sample 20 is that my t-score is going to be different. That t-score is found from that t-chart. We go to the 95% column. That, of course, would be 0.025 column. We have 19 degrees of freedom. So that gives me a t-score 2.093. So I plug in the 2.093. We have the same standard deviation, 1.3, divided by, this time it was the square root of 20. When we multiply that out, we get 3.8 plus or minus, in this case, 0.608. Notice that that number is different than the 2.55. This is going to be a larger number because of the smaller sample. That automatically makes this interval then also larger, 3.192. I'm going to try and emphasize that it's a larger interval by spreading it out more than what this one is. So it would go over to 4.408. That again should be reviewed. It should look familiar to what we've done in the past. As I mentioned, today we're looking at large sample confidence intervals for proportion. Proportion has some changes. Some of those have to do with our sample proportion, p hat. It is our point estimate, our sample statistic. This would be the symbol that corresponds with X bar that we use for sample means. The other thing that's going to be different is that our adjusted standard deviation for sampling distribution is this expression right here, the square root of PQ over N. That one right there is going to be kind of a challenge for us because that PQ is going to be found differently in different types of problems. And I'm going to give you a bunch of examples on that. Our formula, which we've already written down for confidence intervals, is going to have a z-score in it in all three of these. That's because it's a large sample. Remember, though, the large sample is not determined by n is greater than or equal to 30, but the large sample is determined by these two conditions being satisfied. That will allow us to use a z-score. If either one of these are not satisfied, we cannot use this formula for that, mainly because the sampling distribution will not fit with the central limit theorem. If you recall, for example, in that setting, when I have a proportion, if it's in the middle, the central limit theorem gives us the full normal curve. But when these two conditions, if one of them is not satisfied, frequently it's because either n is too small or more frequently yet, it is because P and Q are close to the edge. For example, if P was way over here, notice that central limit theorem would have part of that normal curve missing. That's why we would not be able to use the central limit theorem properties if these two conditions are not satisfied. As I mentioned earlier, this adjusted standard deviation, that's the standard deviation for proportion. That adjusted standard deviation at times will use the population proportion and its complement, but at other times it's going to use the sample proportion and its complement. Sometimes we have either this available or an estimate of this, which means we would use that first priority. Other times we don't have the population proportion. Frequently we don't have it. And we don't have an estimate of it. Then all we have to work with is our p hat and its complement. P hat again is the sample proportion. It is defined to be X over N. X would be the number of people that are in favor of, say, candidate A. N would be the total number of voters. Q hat is its complement, 1 minus P hat. We'll be using now these. Before I do, I need to review, though, a rule of thumb for determining the value of P and Q. What I'm referring to, I'm going back now to the old slide. I'm referring to whether or not we use this adjusted standard deviation or this one. You've seen this rule of thumb before. Our first preference, you recall, is to use the population or an estimate of that. Most cases, it is not going to be known. Partly that's why we're trying to make a confidence interval, is we don't know P. But sometimes we have an estimate of it or a past history of it, which in those cases we would use that p-value. If none of those are available, our second preference is to use p hat from the sample. That gave me a sample value of the population proportion. In most cases, it is known if we're making a confidence interval. One other snare that you're going to find is if you made a confidence interval and the interval extends over 0.5, that would be a value we would use in those formulas to determine sample size. I'm going to come back to that in about 5 or 10 minutes. Finally, if we don't know a sample proportion, we don't know the population proportion, our third and final preference, kind of the default, is to go back to p equal to 0.5. The reason they do that is when p is equal to 0.5, the product, PQ, will become its largest value. And we have shown that before in one of the last classes before we went on break. If, for example, p is 0.1, q would be 0.9, the product would not be as large as when p is 0.5 and q is 0.5. This 0.5, when plugged into that PQ, gives us our largest possible product. That makes it a safe confidence interval that we would be confident in, no pun intended. Let's take an example. I'm going to give you a moment to read through this before we start. We're looking to make a 99% confidence interval. So my formula, 99% confidence interval, it's going to be for a proportion now. I have 180 out of the total sample size that have used a debit card for this type of purchase. So my formula is a p hat, a sample proportion. Plus or minus is considered a large one. The reason it's considered large is because n times p will be greater than or equal to 5. That is, in this case, I'll be using my sample proportion for that, and n times q will be greater than or equal to 5. To show that, I really need to take that sample proportion, p hat, which is x over n, x being 180 divided by 1252. That sample proportion, in this case, is going to be 0.144, which means q hat will be its complement, 1 minus that, so q hat would be 0.856. If I plug this 0.144 in here, take it times 1252, I will be greater than 5. And if I plug 0.856 times the 1252, it will also be greater than 5. Hence, I know I have a large enough sample. That means it'll be a z-score. And my sampling distribution has an adjusted standard deviation, which in this case, because I don't know anything about the original population, it's going to be p hat q hat over n. That's my formula. So plugging in the proper values now, p hat we found over here, it was this 180 divided by 1252, which gave me 0.144. My z-score for a 99% confidence interval comes again either from our memory, or we take that 0.4949, that's half of the 99, gives me the z-score of 2.575. And then I also am going to use that p hat and q hat in here. So p hat comes from 0.144. Q hat is 0.856. Divided by the square 1252. And I take the square root of the entire fraction here. That's a little bit different than what we did previously. Previously, we just had s here divided by the square root of n. Now the radical goes over the entire fraction. It'll be important that you can work this through your calculator and take it times the 2.575. When you do that, you end up with a 0.026. So now I'll be adding 0.026 to my sample proportion, and I'll be subtracting it, giving me the interval, 0.118, 0.170. That's my 99% confidence interval. What exactly does that mean? It would mean that we are 99% sure that the true population proportion that uses a debit card to make a purchase online is somewhere between 11.8% and 17%. We recognize individuals might be below that or above that, but this is an estimate of the total population proportion that would use a debit card to make a purchase online. This particular example has got an important difference. I've tried to highlight that as what is different in this example compared to the previous one. Go ahead and take a little bit of time to read through that. What is different about this one is that I have a previous value for the population proportion. And I'm looking now to make a confidence interval to see if that's changed. But because I have that one as a previous population proportion, I'll be using that for our P and Q in that adjusted standard deviation. I'm also going to be using that in our NP greater than or equal to 5, in our NQ greater than or equal to 5. So I would have P, which would be 0.2, times N, which would be the 500. And if you could plug that into your formula, you would find that it is greater than 5. NQ probably would not need to be tested because Q would be its complement, 0.8. And if 0.2 worked, 0.8 is certainly going to be greater than or equal to 5. So I know I have a large enough sample here to work with. My P hat, which is X over N, my P hat is going to be the 152 divided by the sample size 500. So when you do that, that P hat turns out to be 0.304. Now I'm going to be looking to find my 95% confidence interval. So my formula, it's a large sample, 95% confidence interval. It's going to be P hat first. That's, again, instead of the X bar, plus or minus a Z score because it's a large sample, times our adjusted standard deviation, the radical over everything. This time, though, I want you to take special note. Rather than P hat, Q hat, because we had an estimate or a historical value of P of being 0.2, I'm going to be using that P instead of P hat, Q instead of Q hat over N, radical going way down. So now plugging these in, P hat, we found over here to be 0.304. My Z-score for 95%, we could show you the chart, but you have it memorized by now, 1.96. And now I'm going to put in these values. P is going to be 0.2. Q would be the complement of 0.2, which should be 0.8, all divided by the square root of N, or in this case, 500. This entire fraction you want to get on your calculator, then take its radical, take it times 1.96. When you do that, again, be very certain that you can come up with this next number. That next number turned out to be, I got to find it here a moment. I'm afraid I did not have that one copied down, so I apologize for that. But I went right to my interval. So you can find it from this interval, 0.269 to 0.339. That's my 95% confidence interval. Let's make sure we, again, realize what this interval means. It means that I am 95% sure that the percentage of people signing up for the new warranty is somewhere between 26.9% and 33.9%. Here's a question now that we want to talk about. Are we 95% certain that the new warranty has enticed more than the historical 20%? Well, the answer to that would be yes, we are, because this entire interval is above 20%. If you're a visual learner, if here is 0.2, this interval went from about 26% up to about 34%. The interval is entirely above 0.2. This interval then is entirely above the historic 0.2. So yeah, we're 95% sure that this new warranty has been effective. It has enticed a greater percentage to use it. Another example. I'm going to let you read through this first. On this example, there is no population proportion that we're given. In fact, we're trying to find a confidence interval to estimate that. We don't have any historical data concerning what this would be. Like if I had found a historical value, say in February, and I'm now looking in March to see if it's changed, I could use that historical value from February. But I don't have anything of that to go on. So all I have to work with is p hat, which is x over n. So in this case, p hat is 110 out of 200. P hat then turns out to be 0.55. I could then also test my NP greater than or equal to 5. In this case, that's p hat, and NQ hat greater than or equal to 5. P hat is the larger one. Q hat would be the one that really needs to be tested, which is the complement of 0.55 or 0.45. So if I plug that in, 200 times 0.45, it will be greater than or equal to 5. It turns out to be 90 actually. 90 obviously is greater than or equal to 5, which means I have a large enough sample. That means that I can use my formula. Down here, 95% confidence interval. It's going to be p hat plus or minus my z-score times that adjusted standard deviation, which again is not going to be PQ this time because I don't have a P to work with. All I have is p hat q hat. Over n. That would be my formula that I need to work with. So plugging in my numbers, p hat is going to be from up here 0.55 plus or minus my z-score for 95%, that was 1.96. P hat is 0.55, Q hat 0.45, all divided by sample size, which was 200. That gives me 0.55. I need to add and subtract this quantity, which this time I do have written down, 0.069. Again, make sure you can get from this set of data down to the 0.069. That means I'm going to take the 0.55 and add and subtract that quantity. So when I do that, I end up with this interval, 0.481 to 0.619. The question we have here is, could we, after seeing this interval, be 95% confident that candidate A would win? 110 out of the 200 in our sample would have voted for candidate A. Our confidence interval is predicting that the true population will be somewhere between 48.1% and 61.9%. So the answer to this question here would be no, we are not confident, because it is possible the true population could be down here at 48.5%, 49%, 49.5%. This interval goes below 50%. And I'm assuming here there's only 2 candidates. So if this goes below 50%, it is real possible that more than 50% would vote for candidate B. So this is not what we would call a sure confidence interval for candidate A. Would taking a larger sample help? Well, the answer to that would be yes. And the reason we think that that might be helpful is because my sample proportion was over 50, it was 55. So if I could get this number right here to be smaller than that difference from 55 down to 50, that would be helpful for us. So that formula, which we looked at on the day before we left, was this formula right here to determine sample size. N had to be greater than PQ multiplied times Z over our allowable error, quantity squared. Again, in this particular one, we're going to talk a little bit about this PQ substitution again. That's a thorn in the side, so to speak, when we're working with proportions. The Z is pretty obvious. It's going to be the same Z that we had here, 1.96. My allowable error is going to be trying to keep this 55 above 50%. So that allowable error that we want to be within is going to be that 0.55, trying to keep it above 50%, which is going to give me an allowable error of simply 0.05. That allowable error is going to come into that formula right here. So substituting in now, I don't have a PQ from the population. I do have a sample proportion, but now notice a little bit, one other thing we're going to talk about. We have an estimate of the population proportion right here. Notice that this estimate goes below 50% as well as going above 50%, which means the true population proportion could very well in fact be somewhere very close to 50%. We don't know that. Because we don't know that, we do know that 50% when put in for P will give me the largest product. So because this includes 50%, I'm going to use the 50 in here. I'm going to say that again. Because this estimate from our interval includes 50%, 50 is what I'm going to use in here instead of the 55. So that P and Q would be 50 and 50. My Z-score is going to be the same 1.96 divided by that allowable error that we found a moment ago, 0.05, quantity squared. Again, I want to remind you it's really easy to forget the square here. So you take this fraction, square it, take it times 0.5 twice over, and what you will end up with is the size of your sample in this particular one turns out to be, N has to be greater than 384.16, which means we always round up to 385. I would have to go back here, rather than 200, run a new sample of 385, find out how many of the 385 prefer candidate A, and if that entire interval would be above 50%, then we would be 95% sure candidate A is going to win. Again, 95% is not an absolute guarantee, but it's a strong likelihood. If it still goes below 50%, we would not be then 95% sure. Just a reference to political elections in our country. Take, for example, a presidential election. There are some states where this interval would be entirely above 50%. If that interval was entirely above 50% for, say, candidate A probably would not campaign that aggressive in that state because candidate A would have been 95% sure that he or she was going to win that election. If the interval went below 50%, we would call that a bubble state. That would mean candidate A would campaign aggressively in there to try and raise that percentage or that proportion entirely above 50%. Those would be referred to as bubble states. We've talked about those before. Some examples of bubble states would be, for example, Ohio. Florida is a bubble state. Actually, Iowa, I believe, was a bubble state in the last election. So those are states that get a lot of campaign advertisements for whatever election you're talking about. A couple of final examples. How large a sample is needed to have a confidence level of 95% and to be certain that we are within 3% margin of error? This is typically one type of Gallup poll. Frequently, Gallup polls will be with a margin of error of 3% or 2%. So let's talk about how large a sample would be used in such a Gallup poll. We're looking at that formula for determining sample size. Again, that formula was PQ over N. I apologize, that's wrong. PQ multiplied times Z squared over E squared. I could have written that also, if I wanted to, as N greater than or equal to PQ. Previously, I went Z over E quantity squared there. You can use either one of those. So let's plug in for this particular one. PQ, again, got to be careful what I put in for that. There's no history here. It's not like we took this test back in February or January and we have some previous history. We have nothing to go on from this problem. So P and Q will be 0.5. My Z for 95% is 1.96. My E, in this case, is my margin of error, 0.03. I'm going to take the 1.96 divided by 0.03, take that quotient, square it, take it times 0.5 squared, and I would end up with the following. N would have to be equal to, in this case, 1,068. Most Gallup polls are around the 1,100 mark if they want to be within 3% margin of error. So you might see a prediction that would say something like this. We predict candidate A will get 57% plus or minus 3% of the vote in state Q. That would mean we would be, in this case, 95% sure that candidate A will be somewhere between 54% and 60%. This would, again, be an example that is not a bubble state. If that prediction had been 51% plus or minus 3%, that would take you from 48 to 54. That would be an example of a bubble state because it went past the 50% mark. They might have listed these as decimals, same overall effect. Finally, if I want to be within 2%, I'm going to go with the same formula, N greater than or equal to PQ, and I have the same Z over E quantity squared. substituting the same 0.5, 0.5 in here. My Z is still 1.96. My margin of error this time is changed. Last time it was 3% here. Now it's going to be the 2% quantity squared. This time I will need 2401. I believe that's what the equality would be. Sorry about that. 2401. So to be within 2%, we need about 2,400 people in that random sample. One of the challenges for the Gallup polls is to get a true random sample that would be unbiased. That's probably their biggest challenge. It is oftentimes why some of their predictions fall into that 5% error factor, is they don't have a true unbiased random sample. They are choosing their 2,400 or they're choosing their 1,100 from a group that would not be unbiased. That's what truly makes a good Gallup poll or not a good Gallup poll. Finally, our last example. The following is a 90% confidence interval, and it goes from 26% up to 54%. They're asking how large was the sample used to construct this interval? Well, where would that come from? That particular sample being used here. First of all, the interval itself. Do you notice that it's going to be some particular p hat plus or minus some particular amount? Well, that amount that we add and subtract, it would have been added to our p hat and subtracted, which means the difference between these two is going to be double that amount, because this interval was found by adding and subtracting. So how far is that plus or minus? Well, I'm going to take the high end of the interval, 0.54, and I'm going to subtract the low end, 0.26. And I end up with 0.28. That means half of that had to be in here, 0.14. Because if I added and subtracted, I ended up doubling that difference. That 0.14 was half of 0.28. So now that means if I take the 0.14 and add it to the bottom, I would get the middle value. That's what I'm going after. That middle value here would be 0.40 plus or minus 0.14. That's how this interval had to have been found. That means that this 0.14 became part of that adjusted standard deviation. For example, this confidence interval, which was p hat plus or minus my z-score times the square root of pq over n. That plus or minus had to be equal to 0.14. So I'm going to take that z times the square root of pq over n. That quantity has to be equal to this 0.14. My z is locked in. At 90%, you recall that z-score was, I have to apologize here, just about made an error here. You double check. No, that z is locked in, and I have to get my memory back. It's 1.645 is the z-score for that. And I'm going to have this PQ. Again, notice because the interval included the 0.5, that's what I'm going to be putting in for P. I am looking for my N. This basically is an Algebra 1 type of problem now where you would solve for N in this case. Turns out if you do that, N will be greater than or equal to 34.5. N would have equaled 35. This particular time, I took this from your confidence interval formula. I could have also used the previous formula that we had for N, which you remember, N had to be greater than or equal to PQ times Z over E quantity squared. I would have gotten the same answer. The P and Q, because my interval contained 0.5, I would put 0.5 in for P and 0.5 in for Q. My Z-score would have been like it was here, 1.645, but I'm going to put that in for this Z. My allowable error was this 0.14 that I found up here, squaring that quotient. N would have turned out to be greater than 34.5 and would have to have been equal to 35. That would be how large a sample was used to construct this particular interval. I think that's the end of our lesson today for section 8.4. 8.4 will be assigned on Monday, the 23rd. It will be due the second class period, which would be on Friday, the 27th. So try to have that turned in by that Friday. You can turn it in later, but then you would get a deduction for being late. Hope this worked out well for our first time. I will get better at this, but I hope it was at least understandable. Have a good day.